In the last lecture, we introduced the concept of Lie groups, and we took a look at a very small number of selected Lie groups. We started by talking about U1, the group of rotations in a plane. This was a very simple Lie group with only one dimension, one parameter, and it turned out to be an abelian Lie group. We next went over to rotations in 3 dimensions, a very important and rather familiar group, the group formerly called SO3. We took a look at its group manifold and found out that the group manifold is really not very simple. SO3 happens to have a doubly connected group manifold, and that leads to some rather non-trivial mathematical results which also have immense physical consequences. We mentioned in passing near the end of the last lecture that SO3 happens to be homomorphic to another group called SU2, which is simply connected. That is to say, its group manifold is simply connected. And SU2 is called the universal covering group of SO3, and as a consequence, we can figure out much of the important properties of SO3 just by using results from SU2, which are actually easier to figure out, despite the fact that SO3 is more familiar and SU2 is a slightly more esoteric group. So what exactly is the group SU2? Now this is something which all of you know, but I'm just mentioning this for completeness. The group SU2 is a subgroup of GL2C, the set of 2x2 invertible complex valued matrices, and these consist of unitary unimodular matrices. That is, matrices U which belong to GL2C, but with the additional properties that U dagger equals U inverse, that's the unitary, and determinant U equal to 1, that's the unimodular or special. So U2 is a group of all unitary 2x2 matrices. SU2 is a group of all unitary unimodular 2x2 matrices. But what exactly is the group manifold of SU2? To understand that, let us now just begin with an arbitrary 2x2 matrix which happens to be in SU2. So let us say that the matrix capital A corresponds to the elements alpha, beta, gamma and delta. Then A dagger, of course, is simply alpha star, gamma star, beta star, delta star. That's simple, you just take the conjugate and transpose the matrix. What about A inverse? Now this is a very standard result in matrix theory and happens to be quite a useful trick to sort of mug up that for any 2x2 matrix, the inverse can be found simply by switching the two diagonal elements and changing the sign of the off-diagonal elements and dividing the resulting matrix by determinant of A. This in itself is nothing great, it's just a special case of the more general result that you all know about inversion of matrices. But for 2x2 matrices, this happens to be very simple to state and also very, very useful. Now, in our particular case, we are talking about an SU2 matrix. That means it's a matrix with determinant 1. So, A inverse happens to be simply delta minus beta minus gamma alpha. Since A dagger has to be A inverse, comparison of the two matrices simply gives us the result that delta has to be alpha star and gamma has to be minus beta star. And putting the two together, we get this result that the general SU2 matrix has to have the form alpha beta minus beta star alpha star, and on top of that you need to impose the constraint that the determinant is 1. That simply tells you that alpha mod square plus beta mod square equals 1. So a general SU2 matrix can be parameterized by two complex numbers alpha and beta as long as their magnitude squares add up to 1. There is no further restriction on it. You can simply change this to a real parameterization just by expressing alpha and beta in terms of their real and imaginary parts. So if you write alpha as x plus iy and beta as u plus iv, then all we see directly is that every SU2 matrix is in one-to-one correspondence with the set of numbers x, y, u, v, but with the restriction that x square plus y square, that is alpha mod square, added to u square plus v square, beta mod square, gives you 1. So, you have a one-to-one correspondence between every SU2 matrix on the one hand and every point in four-dimensional space which satisfies the constraint x square plus y square plus u square plus v square equals 1, which happens to be nothing but the three-sphere S3. Note the sphere embedded in 4 dimensions is actually a 3-sphere because it has exactly 3 degrees of freedom, or it's actually a 3-dimensional sphere. The sphere that we are familiar with, the sphere S2, is actually embedded in 3-dimensional space, but it's a 2-dimensional surface. This is the 3-dimensional generalization of that, and from our experience with 2 spheres, it should be pretty easy to understand that we should be able to shrink any loop on the surface of this sphere to a point continuously without ever leaving the sphere. You can make this precise and write it down in terms of algebraic expressions, but I'm pretty sure the intuitive understanding should be enough to convince you that this can be done. So, unlike SO3, SU2 has a simply connected group manifold, rather than this complicated stuff that you had of a ball of points with the surface having this additional identification of antipodal points. SU2 has a rather simple group manifold, just a 3-dimensional sphere. Now, the reason why we have been mentioning these two groups, SO3 on the one hand, the group of all rotations, definitely a rather familiar thing from our daily life experience, and SU2 on the other, a much more esoteric thing, the group of all 2x2 unitary complex valued matrices, is that the two are connected to each other via a homomorphism, as we have said. SU2 and SO3 are homomorphic. To understand this homomorphism, that is the map which you can have between SU2 and SO3, which preserves group multiplication structure, let us start with something very familiar to all of you from your quantum mechanics classes, namely the Pauli sigma matrices. The 3 sigma matrices, sigma 1, sigma 2 and sigma 3 are very familiar to all of you, and the properties that I have noted down for them are also very familiar stuff. Trace of each of the sigma i's is 0, that is, they are all traceless, and each one of the sigma i's are Hermitian. If you take the dagger, you get the same value back. The product is also pretty well known. If you multiply sigma I by sigma j, you get delta ij I2 plus I epsilon ijk sigma k, where the Einstein summation convention has been assumed in the last term. It's really a sum over k running from 1 to 3, although we have not written down the sum explicitly. This of course follows from the two simple results that each one of the sigmas squared to the identity, and the commutator of sigma I and sigma j is this familiar twice I epsilon ijk sigma k. Now, given these 3 sigma matrices, we can form a matrix by combining them together using 3 components, which we will call 3 components of a vector R, x, y and z. So sigma dot R is simply nothing but the combination sigma 1x plus sigma 2y plus sigma 3z, and using our definition of the sigma matrices, this simply turns out to be the 2x2 matrix z, x plus iy, x minus iy minus z. Now, just like the sigmas, this combination happens to be a 2x2 matrix which is traceless and Hermitian. And a very important result that's going to be very useful soon is that the determinant of sigma dot R, this particular matrix, can be easily seen to be minus x square plus y square plus z square, that is, minus length squared of the vector R. Now, conversely, we can see that an arbitrary traceless Hermitian matrix can be given in this form. It has to be alpha minus alpha along the diagonal. Both the diagonal elements have to be real. Of course, you have to have alpha and minus alpha to ensure that the matrix is traceless. And for the off-diagonal matrices, you will have beta and beta star on the 2 off-diagonal positions. This is, of course, the most general 2x2 Hermitian matrix that you can write down as long as you stick to tracelessness. Now, if you just write down beta in terms of its two real and imaginary parts, mu and lambda, I get this particular form of the matrix, alpha mu minus I lambda mu plus I lambda minus alpha. And this, as you can all see, is simply alpha times sigma 3 plus mu times sigma 1 plus lambda times sigma 2. So basically this is of the form sigma dot A, where A has a components mu, lambda and alpha. So not only is the matrix sigma dot R a traceless Hermitian 2x2 matrix, every traceless 2x2 Hermitian matrix can be written in this particular form. Let us now use that to exploit this connection between SU2 and SO3. For this, let us take an arbitrary element capital U from SU2. This is an arbitrary 2x2 unitary matrix with determinant 1. So, U sigma dot and consider this quantity U sigma dot R U inverse. This is of course the same as U sigma dot R U dagger, and since this is a similarity transformation on the one hand, it preserves the trace, so this resulting matrix must be traceless, and because U inverse is U dagger, it is very easy to see that the resulting matrix here is also Hermitian since sigma dot R is Hermitian. So this is a traceless Hermitian matrix, 2x2 of course, and as we have already seen, every traceless 2x2 Hermitian matrix can be written down in the form sigma dot A for some vector A. So let us call this vector in this case R prime. So there must be some vector R prime in the set of all three-dimensional vectors such that sigma dot R prime is U sigma dot R U inverse. So this tells us that for every U, you essentially have a map connecting R to R prime. Now what are the properties of this map? This map, which I am calling phi U, carries R to R prime, of course defined by sigma dot R prime is equal to U sigma dot R U inverse. The important thing is the map phi U must preserve the length of the vector simply because being a similarity transformation, this transformation which connects sigma dot R prime with sigma dot R preserves a determinant, and the determinant, remember, is a negative of the square of the length. So minus R prime square must be exactly the same as minus R square. Now, in addition to this particular transformation phi of U is connected continuously to the identity. This final characterization, connected continuously to the identity, is a slightly technical one and needs some clarification. Think of it this way. Let us consider a bunch of transformations, not a single one as here, but a bunch driven by a matrix U prime. That is, at any given stage, sigma dot R tilde, let's say, is U prime sigma dot R U prime inverse. And U prime is varied continuously starting from the identity, which is the unitary 2x2 matrix, to the final value U. You can easily do that by constructing any path joining the identity, which by the way is the point 1, 0, 0, 0 on S3, to whatever point on S3 corresponds to your U. And you can think of many continuous paths you can draw between the north pole of S3, so to speak, and the point which denotes your particular final matrix. S3 being simply connected, there is no problem at all in drawing such a curve. And as you keep on changing U prime along this curve, the corresponding transformation between R and R prime also changes continuously. Note that when you started out with U prime at the identity matrix, R prime of course was the same as R, so the connection which you wrote down between them was essentially the identity map. Now what has happened is that you have slowly managed to change this, preserving length all the while until you have hit your final transformation between R and R prime. Now a linear transformation that can do that, preserve the length while staying continuously connected to the identity, is exactly what a rotation is. It should be pretty easy to check that this map between R and R prime is a linear map. All you have to do is just write out the matrices and you will see that has to be the case. And so what we have done is establish that corresponding to every unitary matrix SU2, there is a corresponding R3 to R3 linear map which is length preserving and connected continuous with the identity and hence has to be a rotation. So phi u is a rotation in 3D. It is quite simple to find out the coefficients of the corresponding rotation matrix. All you have to do is start with our relationship sigma dot r prime equals u sigma dot r u inverse. Express that in terms of components, that is, sigma dot r prime becomes sigma j rj prime and the right hand side becomes u sigma j u inverse rj. Here we are obviously using the Einstein summation convention, and we have also taken the rj, which is just a number, across the matrix U inverse. The next step would be to realize that if you were to multiply both sides of this equation with a specific sigma matrix, say sigma I, and then take the trace, then on the left hand side you really have trace of sigma I sigma j rj prime. Again, rj primes are just numbers. They can be taken out of the trace, that is, you can find the trace of sigma I sigma j and then multiply the result by rj prime. And here it's important to realize that sigma I sigma j, the product is delta ij times the identity, the 2 by 2 identity, plus I epsilon ij k sigma k. Once you take the trace of this, delta ij times the identity gives you delta ij times trace of identity, which is 2. On the other hand, the other term, I epsilon ij k sigma k, gives you a 0 trace because all the sigma matrices are traceless. So what you end up on the left hand side is twice delta ij rj prime. On the right hand side, on the other hand, you simply have trace of sigma I u sigma j u inverse. And of course, multiplied by the rj. So the left hand side simplifies further. Remember, there is a sum over j and you have a delta ij, which makes the sum really very simple. So twice ri prime is what you get on the left hand side, and if you divide the whole thing by 2, you get ri prime equal to capital Rij small rj, and you can immediately read off the capital Rij coefficients as half of trace of sigma I u sigma j u inverse. And this means that corresponding to every u belonging to SU2, you can find a unique SO3 matrix, a unique rotation matrix, and whose matrix elements can be simply found out with this formula as written down. So here we have a map which maps every SU2 element into a corresponding rotation matrix. The claim that we are making now is that this particular map phi of u is a homomorphism. The proof of that would simply involve proving that phi of u1, u2 acting on R is the same as phi of u1 times phi of u2 acting on R for every R. And the proof is rather straightforward. All you do is start from the definition. So sigma dot phi of u1, u2 R is nothing but u1, u2, sigma dot R, u1, u2 inverse. Then simply use the fact that u1, u2 inverse is u2 inverse, u inverse. Use the fact that matrix multiplication is associative. You can group them in any way you want as long as you're not changing the order. And the bracket inside in the first line simply becomes sigma dot phi of u to R from the definition of phi of u. And the next step simply gives us sigma dot phi of u1, phi of u to R. And putting these together, it immediately follows that phi of u1, u2 has to be phi u1, phi u2 simply because the equation above is valid for all R. So this is a homomorphism. But the important question is this also an isomorphism? And if you remember our isomorphism theorem that we studied a long way back, a homomorphism between two groups is an isomorphism if the kernel of the map contains only the identity of the domain. Let us check whether that is really correct here. The kernel of this map phi, of course, is the set of all such elements of SU2 for which u sigma dot R u inverse gives you exactly the same matrix back, that is u sigma dot R u inverse, is sigma dot r for every r. And hence the corresponding phi u is the identity map acting on r. So our job is to now determine whether the kernel really contains only the identity of SU2. That is, if u is I2, of course, I2 sigma dot r, I2 inverse is sigma dot r. But the real question is, are there any other values of u for which this equation will also work? Of course, for u sigma dot r, u inverse to be equal to sigma dot r for all r, it follows naturally that this means that u commutes with sigma dot r for all r. Now, in order to see what this tells us about u, let us start with an arbitrary element of SU2, which, as we have seen before, has this particular form. It's a 2x2 matrix with the first row being alpha and beta and the second row containing minus beta star and alpha star, with the additional constraint that alpha mod square plus beta mod square is equal to 1. Now u commutes with sigma dot r for all r. That means u commutes with sigma dot r for the case where r is 1, 0, 0. That is, sigma dot r is simply sigma 1. Indeed, it is easy to see that the statement that u commutes with sigma dot r for all r is equivalent to the statement that u commutes with sigma 1, sigma 2 and sigma 3. So just by imposing u sigma 1 equals sigma 1 u, it's pretty straightforward to do the multiplication. Sigma 1, after all, is a very simple matrix. And if you compare u sigma 1 with sigma 1 u, you immediately see that the condition that follows from that is alpha must be equal to alpha star, that is the diagonal element of u must be real, and beta must be equal to minus beta star, that is the off-diagonal element has to be purely imaginary. Now if this is obeyed, the diagonal element is real and the off-diagonal element is purely imaginary, with the additional constraint of course that their mod squares add up to 1, then such a u will always commute with sigma 1. But our demand is not that u commutes only with sigma 1, u has to commute with sigma 2 and sigma 3 as well. So u sigma 2 equal to sigma 2 u put together by a very similar calculation, which I am not showing the details of here, but is pretty straightforward to work out, will immediately show that you get alpha equal to alpha star once again, but for beta you get plus beta star. So beta should be purely imaginary according to the previous commutation relation, but it has to be purely real according to this one, and the only number which obeys both, of course, is 0. By the way, if you tried using u sigma 3 equal to sigma 3 u, you will again get beta equal to 0. So all these three commutation relations will work together, that is, u will commute with sigma 1, sigma 2 and sigma 3 if alpha is a real number and beta is 0. But once again, alpha cannot really be any real number because it has to obey alpha mod square plus beta mod square equals 1, which means the only possible value of alpha is actually alpha mod square equals 1. Alpha being real, this is the same as alpha squared equals 1. So alpha equals plus or minus 1. This means that the kernel of phi, the set of all unitary matrices which commute with sigma dot r for all r, consists of actually two matrices. The 2x2 identity, which has to be there in the kernel. In addition, negative of the identity is actually also there. Now this kernel, as we have already seen before, is a group. It's a subgroup of the domain. And in this case, it's a group containing two elements. And as we all know, there is only one group which contains two elements, is the group Z2. No matter what the actual identity of the elements are, the group is always basically Z2, the group of two integers 0 and 1 under addition modulo 2. So, according to our isomorphism theorem, SU2 is not isomorphic to SO3 because the kernel is not the trivial kernel. But the second isomorphism theorem actually tells you that if you quotient out SU2 with the kernel, that is, find the quotient group SU2 over Z2, that is isomorphic to SO3. Put in other words, it's really not a one-to-one correspondence between the group SU2 and the group SO3. The particular rotation which corresponds to a particular u can be achieved not only with that u but also with minus u. And that is exactly what the kernel being identity and minus identity together is telling me. By the way, if you have paid careful attention, you would realize that we could actually use the same construction to find a map between U2 and SO3. That is, instead of insisting that my matrices are determinant 1, could just start with arbitrary unitary matrices. All you are doing is a unitary transformation, which is a similar transformation using an unitary matrix. And as a result, the actual transformation that is carried out preserves eigenvalues and so on, and traces. So all that we needed to establish the sigma dot r mapping to sigma dot r prime essentially imposes a rotation on r to r prime, still works for U2. You don't even have to specialize to SU2. But if you were using U2, the kernel would be much bigger, and basically there will be many more elements which map onto SO3. SU2 is much tighter that way. SU2 maps onto SO3 with only 2 elements of SU2 corresponding to each element of SO3. And in that sense, SU2 is almost the same as SO3, but not quite, because of this 2-to-1-ness of the map. Indeed, the similarity of the two groups SU2 and SO3 becomes even more apparent if you just look at their elements which are very close to the identity. Their respective identities, the 2x2 identity for SU2 and the 3x3 identity for SO3. In fact, what we can say is that they have the same Lie algebra. We have not defined the Lie algebra formally for general Lie groups yet in this lecture. We will do that in the next one. For the time being, let me just briefly explain to you what the Lie algebra of SU2 would look like. If you are going to consider elements which are very close to the identity for SU2, you can write a typical element as the 2x2 identity matrix plus a small correction term. And what we are doing here is we are writing that small correction term, which is a 2x2 matrix of course, as epsilon times A, where the smallness is parameterized by this small value epsilon. Now, this particular matrix has to be a unitary matrix. So, identity plus epsilon A dagger, if you multiply that by identity plus epsilon A, of course the identity here is a 2x2 identity, you must end up with the 2x2 identity as a result. And this left-hand bracket becomes identity plus epsilon A dagger, and you're multiplying that by identity plus epsilon A. And if you multiply out the left-hand side, keeping only terms which are first order in the small parameter epsilon, what you end up with is the identity plus epsilon into A plus A dagger has to be the identity. And cancelling out the identity from both sides simply tells you that A dagger has to be equal to minus A. So A has to be a skew Hermitian matrix. Now, A being skew Hermitian is not enough to characterize all the elements which talk about deviations of the SU2 element from the identity. There is one additional constraint that you have to impose on this. In fact, all we have used so far is that my matrix, which is infinitesimally close to the identity, is a unitary matrix. The set of all anti-Hermitian 2x2 matrices would actually end up giving us a Lie algebra of the group U2. In addition to this, I have to impose the constraint that I2 plus epsilon A, this particular matrix, has to have a determinant of 1. That is, the corresponding matrix is an SU2 matrix. In order to do that, what we need to do is calculate the determinant of this particular matrix, and the calculation goes as follows. While there are sophisticated ways of proving the result that we are aiming at here, this one is simple enough for us to calculate the thing explicitly. If I write down the determinant of identity plus epsilon A as 1 plus epsilon small a1 1 plus epsilon a1 2 and epsilon a2 1 and 1 plus epsilon 2 2, that's the matrix. You just take the determinant of that, and when you calculate this up to linear order in epsilon, it is easy to see that you get that just from the product of the two diagonal elements. The off-diagonal element here, of course, contributes to order epsilon square, and even the product of the two diagonal elements has a quadratic piece which we are ignoring for the time being, and the result is simply 1 plus epsilon times a11 plus a22. And if this is to be equal to 1, that immediately tells me that a11 plus a22, which is the sum of the two diagonal elements and has the trace of a, must be 0. So the Lie algebra of Sc2 consists of traceless anti-Hermitian matrices. And the set of traceless anti-Hermitian matrices forms a vector space which is spanned by the three vectors or three matrices I sigma 1, I sigma 2 and I sigma 3. Well, let me just add one thing for the benefit of us physicists here. When physicists talk about the Lie algebra of Sc2, what we typically do is we start by considering this infinitesimally close element to the identity not as I2 plus epsilon a, but I2 plus I times epsilon a. And if you put in an I here, the calculation proceeds in very much the same way, except that you end up with a minus I epsilon a dagger here, and hence the final result is very similar, except that you end up with I epsilon a minus a dagger. And that means finally the demand that we are making on a dagger is that it is actually equal to a. Now that shouldn't come as a surprise, because what used to be called a before is now I times a in this notation, the so-called physicist notation. And what that ensures is that our matrix A turns out to be Hermitian. Now, especially in quantum mechanics, this particular matrix often has observable connotations. In fact, in this particular case, this essentially is the angular momentum operator. If you remember our discussion on the quantum mechanics of rotations in the previous year, you would find that this is essentially what we did there. And because we want to associate Hermitian operators with our observable quantities, we supply an extra I. So, of course, in the physicist version, the Lie algebra of Sc2 would actually be spanned by the traceless Hermitian matrices. The tracelessness still goes through, that's pretty easy to check. And the particular Lie algebra is now a three-dimensional vector space, a linear vector space, which is spanned by sigma 1, sigma 2 and sigma 3. From SO3, let us now turn to another group which is of great importance in physics. This is the Lorentz group, also known technically as SO3,1. This, as you recall, is a group of transformations which transforms four vectors x mu, that is x0, x1, x2, x3, to a new four vector x prime mu. This is a linear transformation, so x prime mu is given by lambda mu nu x nu. Summation convention, of course, being used here, with the additional condition that under such a transformation, eta mu nu x nu, that is x0 square minus x1 square minus x2 square minus x3 square, is an invariant. So this is very similar to SO3 in the sense, in SO3 it's x1 square plus x2 square plus x3 square, which is invariant. Here, the invariance is of a similar quantity, but out of the four squares, one comes with a positive sign and three with a negative sign. So that's the 3,1 in SO3,1. Now, there are other ways of designating this. Many people consider the number of positive things in the signature first, so they would call this SO1, 3. Of course, you could also equally well say that minus x0 square plus x1 square plus x2 square plus x3 square is invariant. These are all equivalent ways of saying the same thing. The question that we have in front of us right now is, just like we could actually get a SO3 transformation, a rotation of coordinates, by using a unitary 2x2 matrix via the U sigma dot R U inverse prescription, can we do something very similar for Lorentz transformations? Note that the reason why things worked there was, if you carried out a unitary transformation on the matrix sigma dot R, it took a traceless Hermitian 2x2 matrix to another traceless Hermitian 2x2 matrix. So the result could also be written as sigma dot R prime, and it kept the determinant unchanged, and the determinant exactly was the invariant that should stay unchanged under rotation. Now, what we can do here is just consider a 2x2 Hermitian matrix and drop the tracelessness condition, so that basically in addition to sigma 1 x1 plus sigma 2 x2 plus sigma 3 x3, what you're doing is adding a matrix with a non-zero trace. This is sigma 0 times x0, where sigma 0 is nothing but the 2x2 identity matrix. So sigma 1, sigma 2, sigma 3 of course are traceless. They don't contribute anything to the trace. It's the I2 term or sigma 0 term which contributes to the trace, into the trace is twice x0. So it's easy to see that the matrix, when you write it out as a 2x2 matrix in terms of components, becomes x0 plus x3 and x1 minus ix2 on the top row, and x1 plus ix2 and x0 minus x3 on the bottom row. And it is very easy to convince yourselves that this is the general form of a 2x2 Hermitian matrix. Remember, in a Hermitian matrix, the diagonal elements have to be real, and two diagonal elements which are real can always be written down in the form x0 plus x3 and x0 minus x3. And the off-diagonal elements are complex conjugates of each other. The trace of this matrix, as we have just said, has to be twice x0. But what is of even more interest to us is the determinant. It's very easy to calculate the determinant of this matrix, and a quick calculation shows that the determinant happens to be exactly the invariant quantity which stays unchanged under a Lorentz transformation. So what we have here in the form sigma mu x mu, a sum over 4 matrices with 4 coefficients, is that you have a general Hermitian matrix, 2x2 Hermitian matrix, whose determinant is what I want to keep invariant. So a linear transformation of sigma mu x mu that yields a Hermitian 2x2 matrix. And the moment the resulting thing is that Hermitian 2x2 matrix, you can write that as sigma mu x prime mu with the same determinant will give a Lorentz transformation lambda from x mu to x prime mu. So to get a Lorentz transformation, all you have to do, Lorentz transformation on the 4 vector x, all you have to do is ensure that the matrix sigma mu x mu after the transformation stays Hermitian and has the same determinant. Now we can always try the same trick that we did a while ago with SO3. Can we try a unitary transformation? That is, sigma mu x mu goes over to sigma mu x prime mu, which is given by u sigma mu x mu u inverse, where u inverse is u dagger. U is a unitary matrix. This looks very promising at first because, as we have already seen, this preserves Hermitianity, and the determinant stays the same because, of course, the determinant stays the same under any similarity transformation. So this has to give a Lorentz transformation transforming x mu to x prime mu. Unfortunately, what it also does, being a similarity transformation, is that it preserves the trace. And the trace, remember, is twice x0. So the fact that the trace does not change under this transformation means that the new 4 vector x prime mu will have a 0th component x prime 0, which is the same as x0, the old 0th component. So this is a Lorentz transformation, but this rather trivially is a Lorentz transformation which keeps time unchanged. In other words, it's just a pure rotation. Rotations, of course, do not affect time at all and leave x1 square plus x2 square plus x3 square invariant, So it obviously leaves the four-dimensional quantity x0 square minus x1 square minus x2 square minus x3 square invariant as well, and is hence a Lorentz transformation. So if you tried using a unitary transformation, just as we did a while ago for SO3, you will not get anything new, you will just get the rotations back. In order to be able to get a general Lorentz transformation, we must think beyond a unitary transformation. How then can we get a general Lorentz transformation? Notice that what we have to do is to ensure that after the transformation, the resulting 2x2 matrix is Hermitian and has the same determinant as the original one, sigma mu x mu. In order to preserve Hermitianity, what we need to do is take a hint from the unitary transformation that we did. The unitary transformation was a similarity transformation, u sigma mu x mu u inverse, but what was really important for us in preserving Hermitianity was that u sigma mu x mu u dagger was an alternative form for that. The u dagger, being the same as the u inverse, was actually of great importance there. So if I just took any 2x2 matrix L without any restriction whatsoever and applied the transformation L sigma mu x mu L dagger on our original matrix, that resulting matrix, as you can easily check, will also be Hermitian and so can be written down in the form sigma mu x prime mu with real x prime mu. However, the unitary transformation had this advantage that being a similarity transformation, it preserved determinants. What we need to do is, we need to preserve determinants without L being a unitary matrix, because as we have already seen, if it is unitary, it only gives us rotations. But for this, let's take a look at what the determinant of sigma mu x prime mu is. By a standard rule of linear algebra, it's just determinant of L times determinant of sigma mu x mu times determinant of L dagger. And note that the determinant of L dagger is the complex conjugate of the determinant of L. So the result is simply mod square of the determinant of L multiplying the original determinant sigma mu x mu. So in order that the determinant be preserved, what I need is determinant of L has to be a pure phase so that its modulus square is 1. So we need det L to be e to the I phi, where phi is some real number. However, for any L, for which the determinant of L is of the form e to the I phi, can construct another 2x2 matrix L prime by multiplying L by e to the minus I phi by 2. And if you do that, this yields exactly the same transformation as L does, because L prime sigma mu x mu L prime dagger has an extra e to the I phi by 2 from the L prime, but it also has an extra e to the minus I phi by 2 from the L prime dagger, and the two phases just cancel each other out. So when we use L prime to carry out the transformation on sigma mu x mu, I end up with exactly the same result. On the other hand, by making this particular choice, we get the same transformation but also ensure that det L prime, which is e to the minus I phi by 2, this factor raised to the power 2 because this is a 2x2 matrix, times determinant of L, which of course is 1. That is of course why we chose the factor to be e to the minus I phi by 2, in order to cancel the determinant of L, if any. So what we see is that rather than using arbitrary 2x2 matrix, if we insisted that my 2x2 matrix has a determinant of 1, I will cut down on many possibilities which would give us the same transformation, and at the same time I will be able to get the same result, that is x mu will go over to x prime mu with the same invariant quantity. So what we can do is we can choose L to be a member of this subgroup SL2C, which is the group of all 2x2 matrices with determinant 1. Now, this map that we have constructed right now is very similar to the map that we used for showing the homomorphism between SU2 and SO3, So this is a map phi from SL2C to SO31. What does phi do? For any SL2C matrix, any 2 by 2 matrix, arbitrary 2 by 2 matrix, no other restrictions apart from the fact that the determinant is 1. For any such SL2C matrix, I get a phi L, and phi L acts on a 4 vector X, so I can think of phi L as essentially giving me a 4 by 4 matrix. It acts on X and linearly produces a new column vector, new 4 vector X prime. And how do I get that? I calculate X prime by using the formula sigma mu X prime mu is L sigma mu X mu L dagger. So this is how we have defined the map phi, and by following exactly the same steps that we did for the SO3 SU2 homomorphism, we can show that this particular map is a homomorphism. And finding out the kernel of this map is also very easy, and a very similar calculation like the one that we did before will show us that the kernel again has exactly two elements, 1 0 0 1 and minus 1 0 0 minus 1. By the way, this should not come as a surprise simply because it's obvious that L and minus L will both give you the same transformation, because you will get two minus signs, one from L, the other from L dagger. And other than that, the way in which we picked out this unimodular matrix out of the general matrix L with an arbitrary phase factor as a determinant was by multiplying it by e to the minus I phi by 2. But you should notice that multiplying it by minus e to the minus I phi by 2 would have produced another matrix L prime, a different L prime, again with determinant 1, and which would do the same job. So it's rather easy to see that for every L which does a job, there is a minus L which does the same job. So the map from SL2C to SO31 is a 2 to 1 map. Two SL2C matrices give you the same SO31 transformation. Of course, the standard isomorphism theorem would tell you that if you quotient out SL2C by Z2, you get a group which is isomorphic to SO31. And this means that many of the properties of SO31 can be understood just by looking at SL2C closely. Just like you can understand SO3, the group of rotations, by looking at SU2 closely. Now, as we have been saying, we will talk about Lie algebras in detail in the next lecture. But we have already mentioned Lie algebras today several times. And essentially, what we have said is we look at what happens very close to the identity of the group. Now, if you want to take a look at SL2C, at least very close to the identity, you can try writing a general SL2C matrix as identity plus epsilon times T. The epsilon is here simply to keep track of the fact that this is a small quantity, so that you will only calculate things to first order in epsilon. The determinant of L can easily show by a very similar calculation as the one that we did a while ago, is simply 1 plus epsilon trace T. And so the unimodular restriction that SL2C only consists of matrices with determinant 1 translates to this demand on the infinitesimal displacements away from the identity. That is, each of such matrix which characterizes the displacement has to be traceless. The collection of all such matrices together form the Lie algebra of SL2C. Although, once again, we have not formally defined the Lie algebra yet, but as we have already said several times before, in the case of U1 in an earlier lecture, or in the case of SU2 just a while ago, the basic idea is you just look at what happens very close to the identity, how you can move away from the identity. And here the movement is given through matrices, 2 by 2 matrices, and which together form a vector space. These are all traceless matrices. It's pretty easy to see they form a vector space. They are 2 by 2 complex matrices, and small SL2C, this is a notation which stands for the Lie algebra corresponding to capital SL2C, is nothing but this vector space formed of all these traceless 2 by 2 matrices. Now, a 2 by 2 matrix has 4 elements obviously, but the traceless demand cuts down the number of independent elements to 3. But these are 3 complex numbers in general. And so what we have are 6 real parameters. And you can easily see that SL2C is a 6-dimensional real vector space. This is important. This is not a complex vector space that we are talking about right now. We are talking about a 6-dimensional real vector space, and it is spanned by traceless matrices. Sigma 1, sigma 2, sigma 3 are already traceless matrices that we know about. But there are 3 more traceless matrices which are independent of these. Independent in terms of real vector space. That's I sigma 1, I sigma 2, I sigma 3. That's one choice. There could be other choices, but this is one of the most convenient choices. You might argue that I sigma 1 is dependent on sigma 1. It's a multiple of sigma 1. But note that if you're thinking of a real vector space, the only things you're allowed to multiply by are real numbers. So I sigma 1 and sigma 1 are actually independent matrices when you think of them as elements of a real vector space. A real vector space does not mean that the elements that make it up are real numbers or matrices with real coefficients only. A real vector space is a space where the scalars that you use to linearly combine different vectors are only taken from the set of reals. So in that sense, sigma 1, sigma 2, sigma 3, I sigma 1, I sigma 2, I sigma 3 give us 6 independent matrices which can together give you any small SL2C matrix, that is any matrix which is traceless. And much of SO31, much of the theory of SO31 and the corresponding, this is the Lie algebra SO31 that I am talking about, and the corresponding Lie group, capital SO31, can be figured out by essentially seeing that what we have here are 2 copies of basis vectors for SU2. You have sigma 1, sigma 2, sigma 3. On top of that, you have I sigma 1, I sigma 2, I sigma 3. Essentially, SU2 twice. And this is very, very important. This is what gives us all kinds of special objects like dotted and undotted spinors and so on. Things which we talk about in, say, things which play a very important role in the subject of supersymmetry. We are not talking about all those things right now, but it is important to understand that somehow in the theory of Lorentz group, 2 SU2 groups are hiding somewhere. And using those SU2 groups, we can draw many important conclusions about the representations of the Lorentz group. We will see this in some detail later on once we get more machinery in place. Let me wrap up this lecture by talking about a group which is of immense importance in particle physics especially. This is the group SU3. It is a subgroup of GL3C, that is the set of all invertible 3 by 3 complex valued matrices. This is of course the subgroup which consists only of the unitary matrices, that is for all the U's which belong to SU3, U dagger equals U inverse, and the S as always stands for special, that is unimodular. So determinant of U has to be 1. As I have said, the group SU3 is of great importance in particle physics especially, also in other branches of physics, but mostly in particle physics. And there, most of the calculations that we carry out involves not really the group so much, but more its Lie algebra SU3. And as we have been saying, we have not formally defined a Lie algebra of a group yet, but we have essentially said exactly how to figure out the Lie algebra. All you do is look at infinitesimal transformations, that is transformations which are infinitesimally close to the identity, and see what deviations you have from the identity. These will form a linear vector space which actually gives you the basic Lie algebra. So for this SU3 group, we play exactly the same game as before. And once again, because this is a very, very important group as far as physics is concerned, let us put in the I in the deviation, as all phases do. So U is taken to be I3, the identity, plus a deviation which depends on the small parameter epsilon, but I write that as I epsilon times another 3 by 3 matrix capital A. And by following exactly the same route as before that we did for SU2, we can easily show that here this particular form of the deviation implies that A has to be Hermitian, that is, A and A dagger have to be equal to each other. So, the matrices which inhabit the Lie algebra of SU3, small SU3, are all Hermitian matrices. By the way, if I had followed the mathematician's convention of not including the I in the deviation, then the same Lie algebra would have been considered to be the Lie algebra of anti-Hermitian matrices. It's just a matter of whether I include the I in the parametrization or in the matrix itself. This is not the only constraint, however, as you must have realized. All that A equal to A dagger ensures is that the matrix U is going to be unitary, at least to first order, in the small deviation parameter. However, we also have the determinant of U equals 1, and for this we can use exactly the same method that we used before, that is, write down U as a 3 by 3 matrix with identity plus small correction terms, and it's pretty easy to show by a direct computation that the determinant will then come out to be 1 plus I epsilon times trace of A, plus of course higher order terms, but we are ignoring them anyway. So in order the determinant of U turn out to be 1, what you need to impose is the condition trace of A equals 0. So the Lie algebra of capital SU3, that is the Lie algebra small SU3, consists of traceless Hermitian 3 by 3 matrices. So how many such independent matrices can be there? Note that because you are insisting on Hermitianity, all the diagonal elements of these matrices should be real. So that gives me 3 parameters. When you go on the off-diagonal side, there are 6 off-diagonal elements, but of which 3 are complex conjugates of the other 3. So knowing any 3 of them would give us all of them. So what you need are 3 complex parameters, but in terms of real parameters, that would be 6. So if we were just insisting on Hermitianity, there would be 9 parameters which you would need to describe an arbitrary matrix of this set. On top of this, however, you have this condition of tracelessness, which means that the 3 diagonal elements cannot be independent, they have to add up to 1. So basically what you end up with is 8 parameters. So to describe a typical matrix in small SU3, you would need 8 parameters, and that obviously implies that SU3, this vector space SU3, the Lie algebra that is, has to be an 8-dimensional vector space. Now there are of course infinitely many different possible bases which I can write down in 8-dimensional vector space, but a rather obvious generalization of the SU2 basis vectors suggests itself when I try to write down a general matrix in SU3. So note that the general SU3 matrix would have diagonal elements which are real and off-diagonal elements which are complex conjugates of each other. So if you look at the top corner, the top 2 by 2 corner, you can clearly see the standard SU2 matrix sitting there, written in red. So A3 minus A3 down the diagonal, A1 plus IA2, A1 minus IA2. If you come below that, you have A4 plus IA5 following the same pattern as we used in SU2. Of course, if A4 plus IA5 is sitting in the 3-1 element, the 1-3 element has to be its conjugate, A4 minus IA5. The 3-2 element, A6 plus IA7 gives you A6 minus IA7 as a 2-3 element. In addition to this, you have one more freedom, that is, you can actually add any set of numbers to the diagonal as long as they add up to 0. And that is exactly what we have done here. We have chosen a specific combination 1 by root 3 a8 plus 1 by root 3 a8 minus 2 by root 3 a8. This is just one convenient choice. Why the 1 by root 3? Why this 1 1 minus 2 precisely? Why not something else like why not 1 0 0? That's simply because of convenience which follows in the equations if you choose this particular basis. This is something we will see in more detail when we try to actually do calculations with the SU3 algebra. But once we have written down the general 3 by 3 Hermitian traceless matrix in this form, it is rather obvious that we can write down basis matrices from this. All you have to do is take coefficients A1, A2, A3, etc. and write this general matrix as A1 times lambda 1 plus A2 times lambda 2 plus A3 times lambda 3 and so on. And this immediately gives me this particular choice of 8 basis vectors. Note that lambda 1, lambda 2, lambda 3, if you look at the way in which we wrote down the top square or top 2 by 2 piece with the SU2 algebra sitting there, it's obvious that lambda 1, lambda 2, lambda 3 are direct generalizations of the Pauli sigma matrices to 3 dimensions. In fact, lambda 4, lambda 5 are also very much like sigma 1 and sigma 2. And lambda 6, lambda 7 also plays exactly the same role. Lambda 8 is a diagonal correction term, 1, 1 minus 2 down the diagonals with 1 by root 3 as an overall factor. The fact that the SU2 matrices are hiding very plainly in this representation actually is not an accident. As we will see later, the SU2 algebra plays a huge role in the study of not any, but almost every Lie algebras. In the theory of a special class of Lie algebras called semi-simple Lie algebras, the SU2 subalgebras which they have play a very, very important role. We are going to explore them in a lot of detail later on, but for the time being, you should appreciate that it is pretty easy and straightforward to find out the basis vectors for the small SU3 Lie algebra. The physical consequences of this, how these makes predictions about, say, the quark model or about quantum chromodynamics, etc., are things we are going to talk about in later lectures. For the time being, let us wrap up this lecture. We will talk about Lie algebras, especially for matrix groups, in some detail in the next lecture, where we are going to see that some of the results that we have seen in this lecture and the previous one are really special cases of much more general things which occur in many, many other different contexts. Till the next lecture. Bye.